Okay, the next presentation. Next presenter is Dr. Shan. Dr. Bao is the Associate Research Scientist of the University of Michigan Translation Research Institute. And she was also appointed as an Associate Professor in the Industrial Manufacturing System Engineering Department and Civil Engineering Departments of the same university. She'll deliver a presentation titled On the Examination of Teen Drivers, car following behavior under naturalistic driving conditions with and without an advanced driving assistance system. Dr. Bao, please start sharing your screen.
Yes. Okay, can you see my screen?
Not yet. Okay, can you make it full screen?
Yeah, it's coming up.
Okay.
Okay. Is it full screen for you?
Okay, looks perfect. Thank you.
Okay, great. Oh, first of all, good morning, good afternoon, good evening. So I want to thank Professor Huang, Professor Li, give me this opportunity to basically share our study on the teen drivers car following study on the naturalistic driving conditions with and without ADAS system on behalf of my co-authors. So Dr. Li has already given an introduction of my background. So basically, before I started talking about this specific topic study, I want to share some of my current research work with all of you. So my background is a human factors engineer. So I have done quite a set of work related to human factors issues in automated driving. So the first topic in this area is basically I have done work related to ADAS prototype as well as a production system evaluation to evaluate and examine how the system and the driver behave and perform under different scenarios and conditions, especially challenging scenarios, whether there are unexpected safety consequences, as well as to connect user opinions and their acceptance. So the second topic in this area is related to the AV communication and interaction with other road users, because we know the introduction of the automated vehicle technologies, the ultimate goal is to improve the whole transportation system. So currently, the part of interaction between AV and other road users, especially vulnerable users like pedestrians and bicyclists, is still of the bottleneck of this technology development. So I'm currently working on several projects related to how to design the system better to assist this communication and interaction. So the third topic I'm currently working on is related to driver state detection and prediction, because we know based on the SAE definition, level 1, level 2, level 3 systems, they still need to keep the driver in the loop. So I have conducted work related to develop algorithms to use different vehicle kinematic features to predict driver state, as well as to develop the warning systems to keep drivers in the loop. And the fourth topic I'm working on is basically related to the user trust and acceptance in AV technologies, because we know the ultimate goal we develop AV technology is basically we want our users to use them. So how we can basically develop a better measurements and to quantify the user trust and to promote the user trust is basically one of my research topic currently ongoing. And the last but not the least topic in this area is related to user training and education, because we know most of our users still naive users in the AV technology. If you ask a Tesla owner, so what is the SAE level of autopilot system, what is the assumption when you can use them, when you cannot use them, probably I would say 90% of the Tesla owners cannot tell the answer correctly. So the diagram I'm showing here is a list of the methodologies I have used in all the studies that I have talked about. So generally speaking, it's a data-driven methodology. So I have done crash data analysis, survey data analysis, simulator-based study, on-road study, naturalistic driving study, and data mining, and computational as well as software simulation by leveraging the virtual reality technologies. So in the next couple of slides, I will give you some example studies to elaborate how we use the different methodologies. So again, in the ADAS evaluation study, I have done work related to evaluating crash warning systems level 1 to level 4 ADAS, as well as the ADS system, which is called automated driving system. So there's a difference between ADAS and ADS. So that's a quiz for everyone here. And also I have done evaluating the eco-routing app development as well as the examination and the seatbelt interlock. So these two are not necessarily ADAS systems. The same restrictions, but however, even you have pretty restricted requirements, they're still quite the average seatbelt use rate in the United States is about 90%, but there's still 10% of people under some circumstances, they do not use the seatbelt. So we conducted this naturalistic driving study to understand why they are not using the seatbelts, as well as whether the interlock system will improve their seatbelt use behavior. So the other couple of studies I want to show quickly here today is related to the communication and interaction between AVs and vulnerable users, basically it's pedestrians and bicyclists. So here you see is an ongoing study sponsored by M-City. I have the fortunate to work with a group of wonderful liaison people from the lead companies, industry representative on this exciting topic. So basically, at the University of Michigan, we deployed a level 4 Navia shuttle bus in the Ann Arbor campus. So the level 4 shuttle bus, there is no steering wheel. It's basically running along a predefined routing on the public roads. So my project is basically to mining these data to look at different sensor collected. There's a mobile sensor, there is a LiDAR collected sensor, radar data sensor, to look at when the automated shuttle, autonomous shuttle encountered different groups of pedestrians, whether it's a single pedestrian or group pedestrian, what is the reaction from both, what is the speed trajectory from the AV side as well as the speed and other behavior from the pedestrian side. So we have found that my group has developed different algorithms to estimate the speed of both sides, and we have found the speed is actually on a lot of conditions is a good indicator of the communication between these two parts. And the other study I just will briefly mention that is sponsored by Toyota Research Institute to look at mining the existing naturalistic driving study data to look at how the human driver take over the bicyclist, because we know that overtaking bicyclists, the number is the leading fatality scenario for bicyclists on the US roads. So we are trying to understand that of different road conditions, road infrastructures, whether there is a dedicated bike lane or not, how our human drivers overtaking the bicycles, then how to get a reference for the future AV design. And the results is published in AAP. So I'm a really big fan of our AAP journal. So that's just a brief introduction of my current research work. So back to the real topic tonight is about how the teen drivers behave when compared to adult drivers with and without ADAS features. So basically, some of the statistics right here, right? Background, we know the teen drivers are overrepresented in the road crashes in the United States. So they're having a lot of studies investigate why the teen drivers have these very high crash rates. So studies have identified, generally speaking, they are immature and they lack of skills and experience. And also there is a greater potential tendency of conducting risky behavior like speeding, tailgating, and more likely to use cell phones while driving. So then we have all these wonderful, great automated vehicle technologies, ADAS features, ADS features. So the question is that with this introduction, will this system help to improve the safety of the teen drivers? So that comes to the study objective of my topic tonight is that we are interested in examining the age-related differences among 4 age groups, including teen drivers, specifically 16 years old, younger between 20 and 30 years old, middle-aged 40 and 50 years old, and older drivers between 60, 70 years old during highway car following. What's their natural following behavior on the highway in the United States? And we're also interested, the second objective is to investigate whether and how an integrated in-vehicle safety system would impact on the driver's following behavior, especially for teen drivers, because there are relatively a lot of more studies have conducted on adult drivers, but not on the teen drivers side. So the methodology is that we use the 2 existing naturalistic driving study data sets that conducted by University of Michigan Transportation Research Institute. One is the US DOT sponsored study, the integrated vehicles based safety system study, that in that particular study, we had 108 adult drivers equally from 3 age groups. And the second data set that we VBS study, as well as from the 20 teen treatment drivers baseline study. Then we used the following 4 weeks of treatment from the 108 adult drivers, as well as the 20 teen drivers. So I just love to show this feature because it's just we are proud of the history of work we have been working on. So the University of Michigan Transportation Research Institute has a long history of conducting the ADAS and ADS research, can trace back to the 1990 that we were working with. I was not there yet, but I'd like to say we were working with AMTI folks who were working with GM to develop and testing the first generation of ACC adapt cruise control system. Back that time, it was called intelligent cruise control, which is ICC. So then we have a lot of ADAS NDS FOT studies have been conducted until today, like level 3 systems evaluation. So here's one example about the teen driver study from the teen IBBS study. As you can see that the drivers was driving using one hand, and we have 4 different cameras that capture front view to rear view, as well as the driver up torso. So in this video, basically, I'm just gonna play one more time. The teen driver was distracted by her phone. She was checking the road but then she thought she was okay, but didn't expect that the lead vehicle braked. Then basically she crashed into the lead vehicles. So under this situation, we would understand that if there is a crash warning system, that could definitely avoid these situations. So these are all the vehicle kinematic features that we collected and displayed here. So because we are interested in comparing the teen drivers' car following on the highway drive during the highway driving to the adults, so that's we basically first step is to identify, define the steady state following events. So then we compare all the different behavior measures during these following events. So here's the list of the credentials that we used in this study as well as the past studies. So I'm not gonna read these, so it's also in the paper. So if you have any questions, you're welcome to ask me. So based on these definitions, so we basically totally find a total of 35,099 following events coming from 125 drivers. So that basically composed of 105 adult drivers and 20 treatment teen drivers. Remember, even we have 40 teen drivers in total, but only 20 drivers had the crash warning systems from 4 age groups, representing over about 40,475 miles. So in the figure diagram, you can see here, so the teen drivers, because they were only 16 years old back that time when they participate in the study, so their driving mileage are relatively very low compared to the other 3 adult drivers. So the middle age, because who needs to work, who needs to commute every day, actually contributed to the most driving mileage. So the dependent variables we look at in this study include the mean value of 5 car following performance measures, including time headway, acceleration value, and the deceleration value, closing speed, as well as the host vehicle speed, because it's following, there is a lead vehicle as well. So we also look at the proportion of the risky behavior, which is defined by the proportion of the tailgating during the car following, which is the time headway less than 1 second. That definition is from previous study as well. And then we also look at the proportion of all the 125 drivers, their speeding behavior. So basically the speeding in Michigan roads, the posted speed limit on highway is about 70 miles per hour. So we define as 75 miles. If it's greater than 75 miles per hour, which is about 33.5 meters per second, that's called speeding. So then we use a linear mixed model to analyze the data with all the independent variables of age and gender, traffic density, driving time, etc. So here's some brief results. So this is the mean time headway. We look at there's a significant age effects that in terms of the mean time headway maintenance during the steady car following events. And we also found the interaction effects between age and gender were also significant. So specifically, younger drivers had the shortest mean time headway, while older drivers maintained the longest mean time headway, which is also consistent with the literature. Generally speaking, studying on the older drivers, they are more conservative compared to the other age groups. So our study just further confirmed that among all the 4 age groups, that older drivers still the most conservative in terms of the time headway maintenance. We also found that teen males differed from female drivers that with a longer mean time headway. That's kind of interesting out of our expectation though. So we were interested in the system effect, because we want to know that during the treatment, whether the drivers were more likely to keep longer time headways. So interestingly, we did not find a statistical significance in terms of experiment effects. However, when we look at the weekly effect, week by week, so if you recall, we had a total of 4 weeks of treatment data and 2 weeks of baseline data. So the week 3 is the start of the treatment week that we found that they had a sudden increase of the time headway when they firstly get the crash warning system. However, with more time going on, more exposure to the system, especially the second week. So second week and the third week having the system, they gradually become into their natural behavior. So their time headway is dropping. So in terms of the acceleration deceleration value, we also found that age group was found to have a significant impact on mean value of the acceleration value. So basically there was a great mean deceleration value in teen and younger drivers when compared to middle-aged and older drivers. So here again, it's just basically to show that relatively speaking, teen and younger drivers use the pedal more harshly compared to middle-aged and older drivers. Again, we did not find the differences between the teen and younger groups. And we did not find the system effects either. So in terms of the speed of the host vehicle, we did not find a significant age-related effects. We found, generally speaking, male drivers basically drive faster compared to female drivers. And again, we did not find significant effects of the experiment on the host vehicle's speed. There is also a weak effect, a similar weak effect that in terms of the speed showing here. So in terms of the proportion of risky behavior, so that is featured by proportion of tailgating behavior as well as the speeding behavior. So we found that there are significant age-related effects. So age group revealed significant effects on the proportion of tailgating and speeding. And younger drivers had the highest proportion of tailgating and speeding. So again, we did not find statistical evidence to show there is a significant effect of the system on changing the driver's driving speed during the car following events. So we also look at the driving time effect in terms of it's a daytime or nighttime. So interesting, we found that all the adult drivers generally drive more conservatively during nighttime. So in terms of they had longer mean time headway and less value of the acceleration, and drive a little bit slower during the nighttime. However, teen drivers did not show such effect. So in conclusion, so basically we found significant age-related differences for sure in terms of the car following behavior on the highway. So generally speaking, teen drivers and the younger drivers showed the most potential risky behavior when following. And also the adult drivers tend to do some compensation behavior when driving during the nighttime by driving slower and follow a little bit further, but no such a compensation behavior was observed in the teen drivers. And the most interesting point is that we did not find that the use of a warning system shows statistical impacts, significant statistical impact on the driver's following behavior. So, so basically 2 parts, right? So we did not find a negative effects of the system in terms of proportion of the risky behavior. So that means that we did not find the risky behavior increased during the treatment condition. And we also did not find the positive effects of the system in terms of during the treatment, we also did not find the increase of the time headway for the drivers. So that's something to think about. Is that necessarily a bad thing? Not really, right? Because the design of the warning system is basically may not change drivers' behavior in the long term. However, it does make an impact of saving drivers from critical conditions, like the video I just showed. If there is a crash warning system to remind, to keep the drivers to get their attention back to the road, probably they will not, that crash will be avoided. And also we observed some behavior adaptation. So there is at the beginning of first exposure to the system, their behavior will change, but with a certain period of time, their behavior will change back. So there is a future study needs that to check. So these driver adaptation, whether that's going to happen with the level 3 or level 4 automated driving features. So with that, that's my presentation today. Thank you again for your attention. And here's I list all the contact information of me and my lab. So questions?
Thank you very much, Dr. Bao. And I received several questions, but due to the time, we are a little behind the schedule. That is my fault. Okay, I chose one question.
Sure.
Through age division, the study, how did the study eliminate the influence of driving age and the experience on the result of the data analysis? So there might be some novice drivers in adult group and also experienced drivers in the youth group.
That's a very good question. So basically, in the US, probably the situation is a little bit different from China. So basically, so they call the US is the nation on the wheels. So we typically the experience of driving are highly correlated with their driving experience in the United States. And also when we recruit participants, we also have these screening questions as well.
Okay, very good. So I think it's if I were a Chinese student, I would the same question because not many Chinese students are driving here, but most of the American students, they start driving when they are 16, 17. Okay.
Exactly.
Right. Okay, thank you very much. And there are several more questions, and please take a look and you can answer by typing.
Sounds
Thank you
good.
very much.
Thank you.
Thank you very much.